Hello, and welcome to the channel. Today I want to talk about a subject that is very much in conversation amongst engineers, whether it's live sound, mixing for music, post, mastering, all of us have this particular topic in conversation: loudness and TruePeak. Now, there are a lot of papers and articles on the technicalities of this, and some very good websites like productionadvice.co.uk, protoolsexpert.com, aes.org, and many more that have a lot of information on how to interpret the numbers that you see. But what I want to do with this presentation is to break down how this happens behind the scenes. Today, we will be demystifying these terms, loudness and TruePeak. And through this, I hope that as audio engineers, we get a clear understanding of the measuring mechanism. And by that, we also have a very logical approach of how and what techniques to use, how to read the meter in a useful way, and more importantly, we have a clear idea about how the numbers make sense to us. So hopefully at the end of the presentation, you would have understood what these terms are and how they are measured. And I hope to do this in a very simple language that we all understand, and we'll make it as conversational as possible. We will be having a bit of mathematics in this, but we will try and break that down in a very, very simple manner. Because let's face it, we're all audio guys, and all we want to do is give a good mix that sounds really good to the audience. We don't really want to be bothered with a lot of numbers. Right, so what is loudness? Now, if I were to read what's written on the screen, loudness is the characteristic of a sound that is primarily a psychological correlate of physical strength. Now, what is more important to understand in this is it is a psychological correlate. And it is also important to understand that this is a standard definition. But what's the translation of this? It is something that is relative and dependent from person to person. You see, loudness is not just peak level, and that is very important to know. Because if it were, a horse footstep would be louder than a scream. And we all know that isn't the case. Well, we will come back to that shortly, and you will see that peak normalization and loudness normalization can achieve very different results. It is absolutely user judged. But for measurements, we must be able to assign a number to this, because unless we have a number, there is no way we can standardize something. The story of how the number for loudness was achieved is a very interesting one. In fact, it takes into account some of the factors that influence our perception of loudness and combines that into a very interesting form. We have different factors that influence us when it comes to loudness: sound pressure level, frequency contents, and duration. Now, we know each of their effects on us as a person. For example, a high sound pressure level makes us feel the sound is loud. Very logical. A high mid-frequency content makes us feel the same way. Duration is even more interesting. Longer duration of exposure to these sounds actually reduce our perception of loudness as well. So is the opposite effect of having transients. Now, we can take these three components and see how we ended up having a number for loudness. While there are other factors like between listener variables and within listener variables, we aren't taking that into consideration as those are extremely varying values. To this end, it is safe to say that loudness is subjective. Your perception of loudness is not mine. So how did we come up with a value? Let's take a look at this curve and see how we can put a number to them. Now, this curve is the ISO 226-2003 curve. Now, this is the modern variation of the Fletcher-Munson curve, or the equal loudness contour. I'm pretty sure that most of us have heard about this at some point in our lives, but we've not really paid a lot of attention to it. Don't worry about that. We'll see how this makes a lot of sense in a much simpler way. Now, the first step to put a value to something is to standardize it. Now, how do we standardize something that is completely subjective? Well, we use the fact that it is subjective and extend it. How? This is where we can use phones. Now, what's a phone? A phone is defined as our perception of the intensity of a 1K pure tone at a given SPL. So, for example, when I say 40 phones, it means the intensity of what we perceive a 1 kHz tone at 40 dB SPL. Now, For 100 Hz to sound exactly the same way as 1K at 40 dB SPL, we have to boost 100 Hz by 24 to 25 dBs. Now, what happens when we increase this? So let's say we have a level at 80 phones. At 80 phones, you realize that you have to boost 100 Hz by only 12.5 dBs. Now, this gives us a few inferences. First off, we understand that our hearing is not linear and is dependent on the level at which we hear this. Second, it also shows us that we have much more sensitivity towards some frequencies than others. So for example, if you look at the area between 2 kHz to 6 kHz, it shows a dip, meaning we need to reduce the gain to have it to sound equal to a 1 kHz tone. At various levels, our response to frequencies changes, and this is why mixing in a very calibrated space is important. Now, one of the reasons why we chose 79 to 82 dB SPL for small mix rooms is also it depends on the exposure time to these levels, but we will get to that later. If we take the ISO curve and we happen to invert that, we would get a very interesting plot. Now, this kind of relates to an EQ curve that we have inside our minds. Of course, it is not exactly an EQ curve in our minds, but it's just far more easier to understand this and interpret this in that way. Of course, the effect of the curvature of the head as well as the spacing between the ears is important, but we're not going to get into those technicalities for now. So if you look at this curve as an EQ curve that was in your mind, it will show you that you have a roll-off in the low frequencies and you have a bump in the mid frequencies. What that means is whatever signal is coming in, you're cutting off the low frequencies in your mind and you're boosting some of the mids for you to get a perception of loudness. If we take a very similar curve on these lines and we plot that, you would get a curve that looks like this. It has a high shelf boost and a low cut. Now that's interesting. This curve is actually made of two components. The first half, or the low cut, is called an RLB filter. RLB stands for Revised Low Frequency B Weighted. Now there are multiple kinds of weightage like the A, B, C, and D. A weighting has a steeper low frequency cut and is more on the lines of the 40 phones measurement, while the C weighted has a bit more gentler one and is usually used in sound meters. B is not used a lot today, while D is used for aircraft measurements. That's because at higher levels our response to frequency is quite different and hence the weightage will change. And you'll see the second half is called a pre-filter, which is more like a shelving boost. It reaches around 4 dBs high at around 4 kHz. Now the combination of both these filters is called a K-weighted filter. This is how frequency content is taken into consideration and made a measurable value. Now, it is also interesting to note that this filter was originally designed at a sample rate of 48 kHz. So for higher sample rates, the equation had to be interpolated to be able to achieve the same values for this. There is a very interesting AES paper, a convention paper numbered 10064, and that provides a very interesting interpolation for this. But we'll get to that in a bit, and we'll find out why I actually mentioned this little value over here. So now that we have the filters, the basic process for the measurement is simple. The signal is passed through the K filter to account for the properties of our hearing, wherein we've just seen that we have lesser response towards low frequencies and a higher response towards high mids and above. From this, the mean square is taken to measure the power. So you can see that what we are measuring is actually power in this case. And the amount of length of time that we use to measure this power is 400 milliseconds. This means that the samples in 400 milliseconds are taken and the mean square is calculated for this. This value is then converted to a dB scale. This resulting dB scale value is then averaged over the entire time of playback as it goes on. This average happens in the integrator part. So to put it in simpler terms, we take the sound, calculate the effect our head and ears have on it, and average its energy over the playback time. This is how we capture the third component that affects our loudness perception, duration. So we've taken SPL, we've taken frequencies, and we've taken duration. Well, that's cool. So where's the loudness? This is the mathematical expression for that. Now I know it looks daunting, but this equation can be converted into a very simple human-readable form. As an audio engineer, you would never ever have to come across this equation in your life. But it is also very interesting to see how such an equation is formed. And there's a lot of beauty in this, where this equation actually takes something that was very subjective and converts that into a number. But by breaking down this equation into a form that we can all understand, this will give us a lot of very interesting insights into how we can use many different processors in order to achieve a certain loudness spec. And why do we need to understand what these strange symbols do? Well, the answer to that question will hold the key in understanding how to deliver and listen to a mix without forcing ourselves to look at meters constantly. Because let's face it, we are audio engineers and artists first. You shouldn't be held back by numbers. And just in case we go overboard or under, it is this understanding that will help us with mixing tricks and techniques which will get us back into the delivery spec. So how do we make sense of this? Now, the earlier method that we saw has the filter, mean square, dB convert, averaging. It is good, but it can only consider a mono signal. Various studies have shown us that we are more responsive towards sounds that come from the surrounds than the ones that come from the front. Thus, we've added 1.5 dB for the surround channels before it gets to the integrator. So, how are all of these taken into consideration? Each channel follows a chain of processing up to the weightage as shown in the figure. Now, if you look at this, you will notice that the LFE is not considered as part of the equation because a lot of studies show us that we are not subjected to loudness below 80 Hz. Now, there are people who argue that the LFE should be taken into consideration, and there is also the other school of thought. Now, these signals that we've just measured from the 5 channels, let's assume that this is a 5.1 measurement, are sent into a block that sums the entire values of all these channels together. The summed value is then converted into a dB scale, and this dB scale is averaged over time. Now, if you look at the equation, it is very clear what each component of the equation represents. Now, if we were to convert the equation into a sentence, you would read it as the loudness value is the average of the dB converted value of the sum of the weighted mean square of each channel after we pass through a K-weighted filter. I know that's a long sentence, but if you look here, you can see that this is the power, this is the weightage, this is the sum of the weightage of the power, and the I represents each channel. So if you have a 5.1, I would go from 1 to 5. If you have 7.1, I would go from 1 to 7, etc. This is then converted into a dB scale. Now, what is the minus 691? Well, if you look at the filter, you would notice that the filter is in 0 dB at 1 kHz. So, to compensate for that and offset the filter to be 0 at 1K, we subtract 0.691 to calibrate the filter. Actually, electrical measurements are made at 997 Hz as per the IEC 61606. It has an interesting reason as well, and the simpler explanation is that if one wanted to make sure all the bits are used in the analog to digital conversion when measuring, it is always good to use a signal that is not a factor of the base sample rate. So in the case of 48 kHz, 1 kHz is a factor of the base sample rate. So in all of this case, 997 Hz is the closest prime number to 1 kHz, and that's why at 997 this particular graph is 0. Well, if you take that into consideration, you would also get the whole value of why the minus 0.691 is applied over here. So if you look at this equation, what we are measuring is an average over time of the effect that ears and head has on the energy per channel. And that average is the loudness. And this is how we manage to make sense of the underlying key to how loudness is measured for streaming, broadcast, or OTT. So if you look at this, what this tells you is LKFS is the unit for measurement, and it is called as loudness K-weighted with reference to full scale. Now, the reference to full scale means that the highest value is 0 and every measurement is a negative value below it, which means that you will always see the LKFS at a negative value. The ITU stands for the International Telecommunication Union. Now, it does not give a value or loudness that it should adhere to. This value is actually done by different bodies like the ATSC, the ABU, etc. So they will take this method of calculation and then they will suggest a value that you should have. So for example, Netflix has a particular value, Amazon Prime may have a particular value, YouTube has a particular value. If you're delivering for streaming or broadcast in Europe, you will have a particular value. In the US, there's a different value. And all of these are based on this particular calculation method. This is what the ITU RPS 1770-1 stands for. It means the International Telecommunication Union, the Radio Communication Section, the Broadcast Sector 1770-1. All this is good and was a great method to bring in the three subjective components of loudness, which is SPL, frequency, and duration. Now, remember that the measurement was averaging over time. What this means is that if there is silence, that will be considered as part of the average calculation too. The challenge here was you may have programs that are silent, or you may have title cards or thanks cards in programs. What this means is you have a lot of silence within the program, which means the average actually goes down. And when the program starts, it can probably be very loud and yet hit the spec. This means that one would have to run to the remote more often and the program loudness can be very skewed. This particular factor needed to be addressed. Now, the way that it was done is we introduced a value. It was called a gate. So basically what you have is you have all of the loudness values that come in and enters a gate. The gate is set to pause the measurement if your loudness falls below a given value. So in the case of this, the ASEBU figured that let's keep a value of -8 LU. Now, LU stands for loudness unit. So -8 LU means, let's say, for example, you wanted to deliver something at -20 LKFS. So which means when the program level falls below -28, the meter is paused. And when it starts raising above -28, the meter continues again. This way, silence is not skewing the measurement that you see. So this measurement method, where they had a -8 LU as a gate, was called the EBU R128, and this measurement unit is called the LUFS. After this, the ITU took into consideration all of this, and they changed the -8 LU to -10 LU. And that's how the PS 1770-2 standard came into implementation. Now, there are a few terms that we need to consider when we are reading a meter. Any meter will show you at least these 4 values. You have the momentary loudness, the short-term loudness, the integrated value, and the loudness range. The integrated value or program loudness as it's called. What is key is the way or the window of measurement that this is done. The momentary loudness takes 400 milliseconds of a window, and it's a sliding window. We'll see what a sliding window is pretty soon. The short-term loudness is a 3-second measure of loudness. The integrated loudness or the program loudness is the total measure of the loudness. Now, this is a gated measure, which means there are gates that is used in this where the silent portion are not taken into consideration. There is also one more value called the loudness range, which is a very different method of calculating the loudness range of a program. There are 2 schools of thought to the loudness range and whether it's useful in a musical section or if it's more useful in a broadcast section, but we'll come to that. And when we see how this is calculated, you will see why this debate happens. So let's take a look at how these measurements are done. The image will show you one of the simplest explanations of how MS and I values are calculated. Let's say you have an audio clip as above. The audio clip is divided into blocks of 100 milliseconds each. So the grid lines that you see is 100 milliseconds. Now, in the calculation method that the ITU specified, it said that the block or the chunk of audio for measuring should be 400 milliseconds long. Along with that, it also states that every block should overlap by 75%. Now, this is actually a very easy thing to achieve because when you have something that is 400 milliseconds long, 75% is 300 milliseconds. This is by averaging the LKFS per sample for a time of 400 milliseconds. All of these values that you get right now is called the momentary loudness. This gives us something that is similar to a peak, although technically it is not a peak, but this is easier to compare in our minds because the duration of this is really short. Now, why is this useful? There are two gates to consider. One for silence, which is called an absolute gating, which means anything below minus 70 will be skipped. And as you can see in this, we've already skipped one value over here, which was below minus 70. It's a minus 72 value. Now, there's another value which is called a relative gating. The relative gating is minus 10 LU below the absolute gated loudness level average. What that means is, from this, they will calculate an average, and anything that falls minus 10 LU below that will be skipped. So in our example, let's say the average was minus 25. So anything that is 10 LU below minus 25, which is below minus 35, will be skipped. The average of all of these values is what gives you the integrated loudness level. This is how the integrated loudness is done. So the integrated loudness is actually calculated from the momentary loudness. So what is short-term loudness? Well, short-term loudness is measured in more or less the same way, except that instead of 400 milliseconds, the window is 3 seconds, and the overlap in terms of measuring short-term loudness is 2.9 seconds. That's the difference between short-term loudness and momentary loudness. Now, if momentary loudness is used to calculate the integrated loudness, why do we need a short-term loudness? The whole window that it uses to measure for 3 seconds makes a lot of sense, as it is mostly reflective of a passage or anything that is musically sensible as well. But there's another reason why the short-term measurement is done. The short-term loudness is used for loudness range. So before we look at how this is measured, it's useful to know what is loudness range. You see, the loudness range is not like a dynamic range. Loudness range is actually based on a statistical distribution. Now, if you really want to geek out on that, it's called a probability density function, but you don't really need to go into all of that. So it basically is a plot of all the short-term loudness values that is obtained. So it's also defined in dBs as the difference between the 95% highest value and the lowest 10% value. So, in a layman's term, what is done is it'll take up all of the short-term measurements and arrange it in an increasing order. Now, there are a few steps that it does. Once it arranges all of this in increasing order, you will see how many times it occurs in the program, and that's what is called like a density. So it shows you like, okay, this particular value has occurred a lot of times compared to this particular value or compared to this particular value. And this is called a loudness distribution graph. So the first thing is the short-term loudness is kind of mapped as a loudness distribution graph. From this, we're going to discard everything below 70 LUFS. So everything below this line is discarded. We're not going to consider any of those values for the purposes of calculation. This is where a slight difference happens between the way we calculated integrated loudness. For integrated loudness, anything which was below 10 LU of the average loudness was discarded. In terms of loudness range, we're going to take it as 20 LUs below that. So anything that is 20 LU below the program loudness is discarded in this case. So from this, the LRA is defined as the value that lies between the highest 95% and the bottom 10%. So that's the range. And that range is given in terms of dB value as well. So if you're mixing something for broadcast or if you're mixing something from cinema, the loudness range can be very wide. Cinema loudness ranges can, usually have between 18 or, up to 23, 25 LRAs as well. And that's because the cinema is primarily mixed to conform to a space that's a bit more controlled the noise floors in a cinema theater are comparatively less than what you would have back at home. Whereas if you were mixing with the same amount of dynamic range for something that was to be heard at home, you probably would not hear all of the low-level detailing that was happening, because your ambient noise may probably be higher than the low level that is being played over there. So you don't want to give a very dynamic mix if you were to provide something for the home mixes as well. Now, this is also where I said there was a difference in conversation between the people who mix for music and the ones who mix for broadcast as well. Because when you look at LRA for music, it can be quite unstable in terms of the values. So for music, what people tend to look at is the peak to loudness ratio, or the PLR. There is also another very interesting paper on the PSR, which was presented at the AES as well. The peak to loudness ratio is the difference between the TruePeak and the integrated loudness. The peak to short-term ratio is the difference between the TruePeak and the short-term loudness. If you were delivering a music mix for YouTube or something like that, a good idea would be to have your loudness sections around 3-4 dBs above your delivery spec. So let's say if you wanted to deliver something for around -14, and if you have a very dynamic mix, something that starts quite soft and progresses into a very loud climax as a music piece, your climax can be around 3-4 dBs above your delivery spec, so that when you average it out, the integrated value becomes -14. So let's say when you start, your loudness is around -18 and your climax is around -10. If you have that kind of spec that you can achieve, by the time you average out the mix, it becomes -14. And that's why you would look at the short-term loudness. When you're doing a concert or something, just make sure that your short-term loudness is roughly around 2-3 dBs within the spec, because if loudest portions are going to come towards the end, you need to have a fair bit of headroom for that without hitting the loudness compression that happens outside during transmission. This is probably the simplest way of how loudness is measured. If you take into consideration all that we've seen until now, you have audio that comes in, it goes through the K filter, you get the weighted audio. The weighted audio is split into two. One portion measures the momentary power calculation and the other one measures the short-term power calculation. These progress parallelly, where one will give you the momentary value and the other one will give you the short-term value. These are the M and the S terms. From this, it again continues and checks, is the value more than -70? Yes, then let's continue ahead. This is where one of the difference that happens between integrated loudness and the LRA. So for integrated loudness, it'll check if the value is more than -10 of the average. Whereas for the LRA, it'll check if the value is more than -20 of the average. If it's yes, it continues. The first one averages, or the integrated loudness averages over the entire duration. So from the moment you hit start till the moment you hit stop. Whereas the loudness range will constantly look at a statistical distribution and calculate the difference between the 95% highest value and the bottom 10%. And this is then displayed as your integrated loudness and the loudness range. This is how M, S, I, and LRA is calculated. As you can see, it is dependent on the frequency content, on how long that frequency content exists, on how much dynamics that you have in your mix. This is why when you understand that this is an averaging mechanism based on the frequency distribution in your program, it is much easier to mix something that adheres to the loudness spec. So how would you get used to this? So I've been mixing films, and one of the challenges that I had was, how do you get used to something that is -23 LUFS or -27 LUFS? The easiest way that I found out to do this was to take a mix that is -23 LUFS in measurement and play it back in the room. And I adjust my monitoring level to a comfortable level that I feel is loud enough for me. Because although the -23 and the LUFS values do define something in terms of LUFS, they do not define what exactly it is in terms of SPL. So if I'm sitting to mix and I have a minus 23 LUFS program, I set the monitoring level to a position where I feel that is comfortable enough loud for me. Because some people may be used to mixing loud, some people may be used to mixing soft. So for both of them to be able to have a comfortable delivery spec, this is the easiest method to do. So you raise or you drop your monitoring level to what you feel is comfortable when you listen to a spec that is calibrated. So which that means is the next time you mix, you're going to always hit the spec. An alternate way of looking at this is, if your mixes are consistently 3 dBs louder than your spec, all that you have to do is increase your monitoring level by 3 dBs so that when the next time you mix, you're going to hit the spec roughly. So this is another way that you can interpret how you can monitor from understanding how loudness is measured. So this is the ITU measurement, and this is how replay gain is calculated. Now, replay gain is again taken in terms of things like Spotify and iTunes, for example. So the replay gain uses a variation of the Fletcher-Munson curve. This was first proposed in 2001 by David Robinson, and it uses something that's called a Yule-Walker filter. It is a MATLAB function. It's based on a method called Yule-Walker. If you skip all of those technicalities, a simplified answer to this would be, if you give it a plot, it will be able to tell you what filters need to be used. So in this case, to generate the plot, they needed to have 10 orders of filters so that it matches the boosts and the high frequency responses to this. Now, when they did this with the Yule-Walk, it wasn't really good for the low frequency section, so they first created the Yule-Walk and then they passed the Yule-Walk into a second order Butterworth filter, thereby getting the low cut. So if you look at the way this is measured, you have the audio come in, it goes into a weightage filter, just like the way ITU does it. And then the weighted audio, so difference is the power calculation is done every 50 milliseconds. Now, this power calculation is then sorted in an ascending order, just like the way we saw for the LRA. And from this, it'll pick the highest 95% value of that. Now, that number, whatever it gets, it will subtract this one from the RMS value of a minus 14 dBFS pink noise. So in a way, replay gain is measuring loudness in reference to the loudness of minus 14 pink noise. And if that is negative, it means that the gain is going to be reduced. If that is positive, it means gain would be added. So that's how replay gain works. And replay gain is just basically doing this measurement and putting this number as a metadata into your file. So the next time you play back MP3, if this replay gain value exists and you have soundcheck enabled on your iTunes, it knows how much to drop it down by. So this is the entire calculation of how loudness is calculated. Let's look at how TruePeak is measured. TruePeak is a very interesting concept. The peak that we are usually used to seeing in our DAW is the sample peak. The sample peak just indicates the level of the peak at the point at which the sample is taken. To show that example, what we have here is a 12 kHz sine wave in a 48 kHz sample rate. This is isotope RX, and the reason I'm using a 12 kHz sine wave is because a 12 kHz sine wave is 1/4 of a 48 kHz sample rate, which means there are exactly 4 points of sample in one cycle. Now here's something that's interesting. If you look at the waveform stats, you will see that the sample peak level is -1, which means the highest value at which you have this dot is -1. Now, as long as any of these values don't go above that, your sample peak level is going to be -1. But here's something interesting that happens. If I start moving around some of these samples, you would see that they actually start to interact. Now, even though my sample peak is exactly -1, I have a true peak which is 2.5 dBs. Let's see how high we can go. So you can see that technically, even while staying within the -1 sample peak level, we can still hit a true peak of above 0. And when we start manipulating frequencies which we thought were not really adding to those ones, you would see that they are still completely dependent. and you can technically hit roughly around even values of +6, +12 dBs above zero. Now this is very interesting. If you were to play this, your DAW will never show you a peak indication in that. Instead, what will happen is you will have the sample peak to be -1. But when the D to A conversion happens, there is a good chance that you will have a clip at the output. Now, why is this so hard to measure? Well, if you look at this, logically you would see that the clip happens between two sample points. This is an intersample clip. Now, if the clip happens between two samples, it's safe to say that this is a high frequency content that does not exist in between these samples. So which means that when you do your D to A conversion, this would never show up in a DAW. This would definitely come up at the output of the conversion stage. So how is this measured? If I were to take this and if I were to resample this to 192 kHz, you would instantly see that your sample peak and your true peak are now very closely lined up. So when you have something that is 4 times, you have a sample point that can measure in between the samples. The ITU PS 1770-2 also introduced the method of measuring true peak. Now, as we saw, the true peak is an indication of peaks that can occur between samples. The way we did this was we had to sample 4 times above our base sample frequency, which is if we were at 48 kHz, we did an upsampling to 192 kHz. So the steps that are being done is the signal is brought down by 12 dBs, 12.04 dB to be exact. It's called a 2-bit shift. This one is then oversampled 4 times. So if your base sample rate was 48 kHz, it will be oversampled to 192 kHz. But if the base sample rate was 96, it will just be 2x, which is 192. Then you have a low-pass FIR filter, and the reason you have this filter is to get rid of any spurious frequencies that can occur because of the oversampling. Once this is done, you get the absolute value of the peaks and the maximum value, and this one is then compensated for the 12 dB drop and is shown after conversion to a dB scale. This is how you have the true peak measurement. Now, what changed in the ITU RPS 1770-3 was the FIR filter coefficients for this filter. Now, you may notice that the actual value of the true peak may vary between meters, and that is also probably because the algorithm that is used to upsample may be different. So if you have a spec that requires you to deliver to say -2 dB true peak, it is a good idea to hit a level of -2.3 dB just to make sure that the 0.3 dB of variation is taken into account as well when you have different meters that are used for measuring. So what was there in the 1770-4? Well, it had all of the above values, but it was also extended for a large number of channels. Until now, this was primarily based on 5.1. But at this point, you have 7.1, 7.1.2, 7.1.4, and all the way up and above up to 22.2. So this is, for example, one of the configuration systems that has been used in the measurement. So you will remember that when we first spoke of the equation behind the calculation, we spoke about the I value, which went from 1, 2, 3, 4, etc. up to the number of channels that they were. And this is the reason for that. So if you have any speaker whose azimuth is between 60 and 120, there is a 1.5 dB boost that is applied. If it's not within that, there is no boost applied. So for example, your overheads will not have any boosts applied when the measurement is taken. Now, your loudness is measured based on the channel count or based on your speaker configuration. So if you were to measure, for example, an Atmos mix, it would be quite impossible to measure that because the number of speakers vary from room to room, especially if you're doing a theatrical mix. So the best way to measure the Atmos mix would be to measure the 5.1 down mix of what you're mixing in Atmos. And that is because all of the weightage and all of the methods that we currently have to measure loudness is based on channel count. And Atmos is an object-based padding mechanism, which means that you can have any number of speakers that is there, and the pan automatically renders itself in between those speakers. So the newest version of the renderer actually measures the 5.1 down mix of the Atmos mix that you have. So if you look at the specs that we have at a quick glance, These are the specs. So the 1770-4, for example, defines the loudness calculation. The 1770-1, which is important as well because Netflix uses 1770-1. And if you remember, 1770-1 did not have a gate. So for example, Netflix uses the Dialog gate, and the Dialog gate was developed by Dolby and it was made open source recently. Now, if you look at the algorithm of how Dolby measures Dialog, it's very interesting because it uses a sample rate of 16 kilohertz, and if you understand the Nyquist theorem, you would instantly remember that it is not looking for frequencies above 8 kilohertz. So which means anything above 8 kilohertz is primarily not treated to be as a dialogue. That's why Netflix uses a Dialog gate, and that is being sent into 1770-1 measurement. These are some of the recommendations for short form content. It's the A85 in North America, 128 in Europe, TRP32 in Japan, and OP59 in Australia. You would see that one of the slight changes that happens between short form versus long form is that for the long form content, the short-term loudness is not given as a spec. And if you look at all of these specs, you will see that there is a variation. So for example, the A85 gives you a -24 LKFS with plus or minus 2 dB. There has been a lot of conversations as well as how should you deliver for these specs. So for example, if you're looking at this very interesting chart, which was compiled by Ian Stewart on the Mastering Engineers Facebook page, and this is a very useful reference, and thanks a lot, Ian, for this compilation. Now, there has been a lot of talks on should you deliver multiple loudness values for different streaming platforms. So let's say you're mixing something for YouTube. Now, YouTube, you deliver -14. Whereas for CDs or for commercial playback systems, it's around -12, -9. It varies. CDs are usually taken to be -9. You don't really need to mix differently for different platforms. So if, for example, Deezer is -15 and YouTube is -14, or for example, iTunes is -16, you don't have to deliver all of these different LUFS specs. A variation of 2 dBs is fine. That's why you need to look at the peak to short-term ratio as well. For example, let's say you're delivering for YouTube and your loudness references or the final program loudness that you got is -10. Now, what is YouTube going to do? YouTube is going to drop it down by 4 dBs. So any of these values that you drop down, it's a straight gain change. So YouTube will drop down the value by 4 dBs, which means like you hit a -14 LUFS. What that means is your peaks go down by 4 dB as well. So if you are hitting a peak of, let's say, -0.5, at this point, your peaks would be -4.5. Does that really make a huge difference? It depends. If your mix has a lot of dynamics in it, you probably would lose some of the low content in that. If you look in the loudness range and it is around -8 to -4, is actually good, especially for streaming mediums. One of the reasons is, a lot of people hear this on mobile phones or their systems and they are not sitting in controlled environments, so the ambient noises are quite high. So it's better to give a mix that is not too dynamic, but still maintains a bit of the quality of this. And as you can see, all of this still accounts for the fact of letting transients go through. Because at the end of the day, transients is what makes your mix sound impressive. No one ever spoke about low frequencies as clarity. It's always the high frequencies that are spoken about as clarity. Now, there is one more thing that I wanted to include, and that is the difference between LUFS and LEQM. Now, LEQM, for those of us who don't know what it is a loudness measurement that is used in the theaters. If you look at LKFS, it is loudness that is K-weighted, which is referencing to full scale, whereas LEQM is based on a different weightage curve. It is not a K weightage curve, it's a modified CCIR weightage. And it is equivalent sound level. And this is not referenced to a full scale. So you would see LKFS and LUFS values in the negative forms, whereas the LEQ value is not in the negative. It is a positive value. The M stands for movies, by the way. And it cannot be compared one-on-one. Why is that? So first off, as you can see, they use two different curves completely. So if you were to look at the LUFS ones, you would see that the curve has a boost from around 4K onwards, and it's a 4 dB boost, and that's pretty consistent. Whereas if you look at the CCIR curve, you would see that it goes up to around 6 dBs at around 6K. The other difference is the short-term measurement that you have in the LKFS or LUFS is 3 seconds, whereas in the LEQM, the measurement is taken in blocks of 850 milliseconds, and these are not overlapping, whereas in the LUFS and the LKFS, it overlaps by 75%. One of the reasons it overlaps is in the LKFS or the LUFS calculation is also so that you have a much more smoother loudness representation, unlike it being just loudness representation of blocks. The third difference is a 1K stereo tone at minus 23 dBFS is minus 23 LUFS, whereas a 1K tone at minus 20 dBFS is 85 dB LEQM. The other very interesting difference is that your surround weightage is boosted by 1.5 dBs for the LUFS or LKFS, whereas in the LEQ meter, it is reduced by 1.5 dB. My understanding is the LUFS and LKFS depend on point source surround speakers, whereas in the LEQ, the calculation is taken from an array, and that's probably why you have this difference in weightage. So in some regions, the personal music players, headphones and earphones are manufactured to not exceed a fixed SPL limit according to CENELEC 50332-1. Now, this is a European body that governs the SPL level of your players, and for testing purposes they use a noise which when you measure is a minus 10 LKFS or LUFS, and the requirement is when you use that test tone, no mobile phones or no portable media player should play back that test tone more than 100 dB SPL. So if you look at the speaker based on how these are defined in terms of speakers, small, medium, large, so a small speaker is anything that can deliver below 75 dB SPL. A medium is between 70 and 90. What it is saying is if you have minus 24 LKFS, it should not play back minus 24 LKFS more than 90 dB SPL. So if you look at the test tones used for mobile phones, minus 10 should not play back at more than 100 dB SPL. So which means when YouTube delivers something at minus 14, of course, although YouTube music is not really like pink noise or the test noise, but still, if you had something that was pretty closely related, which would mean that minus 14 LUFS would play back at 96 dB SPL, and that is pretty loud. And the reason you don't feel that is too loud is because you end up hearing these in uncontrolled environments where your ambient noise is much higher. At this point, it is very important that, when someone tells you you need to deliver something at minus 23 LUFS integrated with a TruePeak of minus 2 and your short term at so-and-so value, you exactly understand what it is. And it is not just understanding what it is also about knowing how you deliver to that and how you use the tools that are there in your hands to give a mix that sounds really good, and also understanding at which point should you be concerned about the meters and which point should you not be concerned. But above all of this, it is also quite important that you mix without looking at the meters, because at the end of the day, the audience does not care what the meters are. The audience only cares about the experience. Speaking of those things, these are the different plugins that have the loudness specs in there, and these are the manufacturers that make those plugins. Some of them are free, some of them have certain very interesting values, some of them support the Netflix specs, some of them have a PLR and a PSR value that are being displayed. You can have a look at each one of these. So to round up, what we saw was how is the loudness calculated. It's basically taking the effect of sound that your ears pick up and the effect of your head, converting that into energy, and that energy is being averaged over time. So it's frequency dependent, it is SPL dependent, and it is dependent on time. And we also found out how TruePeak is measured, and we also saw how the loudness range is measured. The loudness range, you may have differences of opinion if you're doing mastering for music, whereas it's extremely useful, especially when you're delivering things for long form, let's say for broadcast. It is not a very stable value. It kind of varies, but if you get it in the ballpark, it's fairly good enough to have a value that translates well for long form content. So this is the breakdown. So if you were to take these things, you would understand that you need to use a TruePeak limiter, And because loudness is averaging over time, you can have a good idea of using compression to reduce the loudness range so that it isn't too dynamic, or you can have dynamic EQs or multiband compressors to tame the harsh frequencies in your sound so that they don't poke out for a long time. Because if you remember, loudness is being averaged over time. So when you tame them just as they cross the threshold, you get a pretty smoother mix in that sense. So you know exactly what to use, how to use, and when to use it. And all of this in a very simple understanding of what loudness is, what TruePeak is, and what LRA is. I hope this has been useful to you, and thank you so much for listening to this, and hope you stay safe and happy mixing.